So okay, so seems like everything is working. So I guess I can start the stream. I'm just gonna have this thing here so that I can see the comments. Okay, so hello everyone, I'm Radoslav, and today I'm gonna be explaining the solution to one of the problems from the lunchtime that passed, like the October lunchtime. And it's the hardest problem, which was solved by, if I'm not mistaken, just 2 people. Let's just see, yeah. So yeah, it was pretty hard. And the problem is the edge flipping one. So yeah, first I'm gonna just like briefly explain the problem statement. So yeah. All right, so basically, first of all, we need to explain what a tournament graph is. And in a way, like, imagine you have a complete graph, and now you choose the direction for every edge. So what this means is basically, if you look at it formally, a tournament graph is basically, it's a definition that's used quite often in general, like computer science. And like you have a tournament graph with n vertices is such a graph that for every ij, such that I is less than j, you either have an edge, a directed edge, which is from I to j, or from j to I. So in a way, it's like a complete graph where you choose the direction for every edge. And like here are the 2 examples of some tournament graphs. One of them has like 3 nodes, the second one has like 4 nodes. And like, yeah, the directions can be random. Also, I mean, like, the following graph could also be possible where like this direction is just in the other, it's just like the other direction. And also, you need to know the definition of strongly connected, which is basically a directed graph is strongly connected whenever from every vertex you can reach every other vertex. Or in other words, the whole graph in a way like just represents a large cycle where it can have like some additional nodes. But yeah, I mean, like, you can find the definitions here in the problem statement. The first one is for basically like a tournament graph, and the second definition is for basically what a strongly connected graph is. So now, in our problem statement, we actually aren't given a graph, but we want to construct one. And like what we are given is just like n, the number of nodes in the graph, and then a sequence of edges. And what this sequence means is that initially we start with this graph that we want to construct, and we check whether it's strongly connected. If it is strongly connected, then what we want to do is like, I mean, if it's strongly connected, then we say that the initial graph is bad. And if it's not strongly connected, we flip the first edge. So we basically flip the edge from A1 to B1. And then we check again whether the new graph will be strongly connected. If it's again strongly connected, then we say that the initial tournament is bad, and we stop. While if it isn't strongly connected, then we continue and we flip the second edge. And we do this so on and so on. So in other words, like, we just sequentially flip the direction of the edge A1 or B, the edge from A1 to B1. So if it was like from A1 to B1, it becomes from B1 to A1, but also vice versa. And like, if the graph is strongly connected before or after this flip, then we say that the tournament is bad. And yeah, in a way, we are given like n, which is less than 400, and like we know that the sum of n's for overall test is like 4000. So this means that we should expect a quadratic solution. And I mean, like, you can notice that we actually have a quadratic output. So yeah, partially that's why the constraints are like that, but we are gonna go into it. And then we are given m, which is the number of, basically the length of this sequence of flips. And I mean, like, you can clearly see that the m increases over the subtask. And the main reason for this is like, basically, the longer your sequence of flips is, the harder is it to actually find an initial graph that will work. Simply because, like, if it's shorter, you have less edge flips and less strongly connected graphs you need to not have. So yeah, I'm just also if you have some questions, just feel free to ask during the session. I'm gonna be like, after some parts, I'm gonna check the chat and like I'm gonna answer some questions. But right now there are no questions, which is pretty good. So yeah, I guess like let's go to the solution. Okay. So again, here we saw 2 examples of some tournament graphs. And like, yeah, basically that's a brief description of what the problem statement asks. Okay, let's look at our main constraints. So we had this m, which is basically the length of the sequence. And like, let's express it as a function of n, just to like formalize stuff, which isn't important, but like, it's not a bad thing. So yeah, in the first subtask, we have like f of n is equal to n minus 2. So in other words, like f of n is just like the length of the sequence. It's just a simple thing. I'm just gonna use f of n as to denote m because, yeah, I just didn't like to write m everywhere. So yeah, for the first subtask, we are given a sequence which has length n minus 2. For the second one, we have a sequence that has length approximately 3/2 multiplied by n, so it's like 1.5 multiplied by n. So, I mean, basically we need to construct a tournament graph that satisfies those constraints. And then for the last subtask, we actually have 2n minus 11. And here, as a hint, maybe before you start reading this solution, the 11 is actually approximately log n minus 2. You can notice from the previous task that we always have this constant, which is minus 2. Here we have minus 3, but it will turn that it's actually this thing sailed minus 2, which is, again, basically minus 2. And yeah, like, you can try thinking about where this log will come from, but also, yeah. And I guess, like, also, those were the 3 subtasks. However, there is also, like, a way to solve this with f of n equal to 2n minus 5. So in other words, like, there is also a solution that will go up to m is equal to 2n minus 5. But like, the analysis of the solution is slightly tedious. In the end, I'm gonna mention where you can see the paper. There is a paper, but like, the elegant solution that's, at least the elegant proof, is for 2n minus 11. So this is, even this was pretty hard apparently to people to find out, so yeah. However, I'm just gonna like say right now, in the end it will turn out that the solution is actually pretty simple. It's hard to actually notice that the solution is correct, and yeah, I hope like I'm gonna give you the main intuition to how to go to the solution. But yeah, overall, how I'm gonna present this editorial would be like, I'm gonna start from the first subtask and I'm gonna build it to the last one, and I'm gonna kind of say what's the transition between each of the subtasks. So yeah, I'm gonna quickly check whether there are some questions before I continue. So, okay, so there was like, what would be the worst complexity on this question? I'm just gonna quickly answer it. As far as I understood, like, I mean, here, I guess, like, given those constraints, what is the worst complexity you can get so that it will pass? Checking the time limit, it's like 1 second. So, I mean, in a way, like, when we have 400, you can easily have 400 cube. So it's like 400 to the 3rd power. So I would say the worst complexity would be t multiplied by maybe n cube should be fine, I think, here, if I'm not mistaken. Although it's, no, n cube will be pretty bad, but like, most likely something that's n squared log will pass without problem. So yeah, if I have to say the worst complexity that will probably pass would be something like n squared cube, n squared multiplied by log for every test. Or maybe like n to the 2.5, which is like n squared multiplied by square root of n. But I mean, when you see the problem, you will notice that the solutions aren't like that. It's more or less, it's hard to get something that's worse than n squared. Okay, so I guess let's go to the first subtask. And I think there were actually quite few people who solved it. And after I explain the solution, probably like you realize how easy it is. But yeah, let's go to the first subtask. So yeah, we have f of n, which is, as I said, equal to m, is equal to n minus 2, which is less than n minus 1. I mean, that's partially why we have n minus 2 and not n minus 1. And like the main observation is that there, in the graph, like imagine we have some other graph which includes only the edges that we will flip. So in other words, like it will just include the m edges we have, like the special edges that we are flipping. And like we have n minus 2 of those, which means that there are at least 2 connected components. Try thinking about it. This is actually a pretty useful fact. You can also use it in some other problems. But like if you have any graph, directed or indirected, and if you have like less than n minus 1 edges, then it will have at least 2 connected components. Strictly less. And that's because if we have n minus 1 edges, this graph will definitely be a tree. And whichever edge we remove, like the tree is the extremal and like in a way the best construction you can get when you have n minus 1 edges, because only when a graph is a tree it will have like 1 connected components. If it's not a tree and it has n minus 1 edges, it will definitely have 2 connected components. And like then if you just remove 1 edge so that you have n minus 2 edges or less, it will definitely like break the tree, so you'll have at least 2 connected components. So yeah, in other words, like if you have less than n minus 1 edges, you have more than 2 connected components. And I mean, like let's just have C1, C2, C3, C4, and so on until Ck. So I mean, like we'll have some other connecting components. And let's just choose C1 as our main component. And construct a graph where we have an edge. So yeah, basically like we have this graph, and from C1 we construct edges to every other component. Like in a way, we look at this vertices in the component of C1. So yeah, we have a bunch of vertices here. And we will construct all of the edges to the other components to be directed like that. So yeah, I mean like in a way we'll have an edge from every vertex here to every vertex in every other component. That's because like we have a tournament graph, so in a way like we have to choose basically we have to choose the directions of every vertex here. And the main observation is that we can't touch the edges that go, basically like we can't really touch those edges because they are not from the ones that we actually flipped. Like again, remember what graph we actually created now. It's just a graph which contains only the edges that were flipped. So yeah, in a way like we have 1 connected component which is C1 and 1 connected component and like the other connected components. And like if basically these edges don't exist, I mean we need to create them in the tournament graph, but like they're not from the edges we flip. So in other words, like if we just fix their direction to be outgoing from C1, then we will never be able to reach anything from C2 back to C1, because like the directions of those edges are fixed to go out of C1. And basically what this means is that we'll never have strongly connected components, because we could reach C1 from we could reach C2 from C1, but we can't go back to C1. So yeah, in a way like C1 and C2 will be in different connecting components. So yeah, in other words, like the solution is very simple. You have a bunch of edges. You have like either you just run DFS, which finds the connected components. You know that we have at least 2 connected components, and what you choose is you just choose a random connected component, and like in the tournament graph, create all of the edges that go out of it to be directed like out of it. I mean like just for every pair of vertices that has at least one of their edges in C1, make the edge from C1 to the other vertex. And you can just print that, and this will give you the solutions to the first subtask, which is 40 points. And yeah, basically that's very simple and trivial. And I guess like, I mean, when you read the problem, it's kind of scary because you can't really comprehend what the problem asks. But like when you start thinking about it, basically how I would say you should approach this problem is that by looking at the constraint. And like you can see that it's n minus 2, which is kind of fishy, because you know that, I mean, in general, like for graphs and trees and connected things, n minus 1 is a special thing, because n minus 1 is the number of edges in tree. And like you see that n minus 2 is less than that. So immediately something that should come to your mind is to actually think, oh, then this means that we have two connected components. So after you actually realize that we have two connected components, the solution just becomes trivial, because you just pick one of them and you create the edges in the tournament graph to just go out of it. So yeah, I hope you understood this solution. I'm gonna look at the questions and I'm gonna wait for a bit, because maybe there will be some. But yeah, it doesn't seem so. Okay, although like the stream has a small lag, so yeah. I'm gonna wait just for a second to see, and it doesn't seem so. Okay. Fair enough. So let's continue with it. Basically, as I said, the first solution is very basic. Find the connected components. We have at least two connecting components. Get the first one and make all of the edges outgoing from it. And this guarantees that you will never have a strongly connected tournament graph from all of the prefixes. Okay. Basically, subtask 2 is actually quite similar. However, this time we won't look for components. We are simply just gonna get like, let's just get like the first vertex. And let's make, in the tournament graph, let's just fix all of the other edges to just go into the first vertex. So in other words, like if we have something like that, I mean, initially there'll be some, so like this is just a part of the tournament graph. All of the edges that have one as part of them will, yeah, basically like that's just part of the graph. And like the initial edges will be from 2 to 1, from 3 to 1, from 4 to 1, and so on until n to 1. And also like we'll maybe have some edges here inside, like from the different vertices. As in a way, like we need to have n multiplied by n minus 1 over 2 edges overall, because it's a tournament graph. And like we may have some edges inside, but like we won't fix their direction right now. We are probably gonna fix this afterwards. And yeah, what will happen if you actually flip one of the edges which are inside of here? So like we have some edge here or something that's like that, and you want to flip it, and so it becomes like that. Well, I mean, you can notice that this means that the graph will still be strongly connected, because right now we have 1 from which we can't reach anything else. So the graph is definitely not strongly connected component. It's definitely not strongly connected. And like if you flip one of the edges that aren't from 1 to something else, you're fine. But yeah, the problem comes when you actually flip one of these edges. Let's look what happens now. So let's call the flips that are basically like that being bad. So like in a way, all of this, I mean like all of this edges which are, all of these flips or edges that are from 2 to 1, from 3 to 1, or just anything to 1 will be considered bad. And like, in a way, what will happen is that if the edge isn't bad, we won't have a change. However, if the edge is bad, so like, in a way, like the algorithm will work as follows. We start from A1, B1, and we go down until like AM, BM. And like after each edge, if it's bad, then we'll possibly change our graph a bit. But like by graph, I mean like this thing, which has like some number of fixed edges. And like right now, the initial edges or the fixed edges are just every vertex to 1. And I mean like, yeah, the first case is a normal edge, or like not a bad edge. And we just keep the graph as it is. That's basically what I explained, because like it doesn't really change the structure or like the strongly connectivity of the whole graph, because I mean you can't really go from, I mean you can go from every vertex to 1, but you can't go from 1 to anything else. So like it's not a cycle because 1 isn't contained in a cycle. But like, yeah, the problem happens when we actually flip a bad edge, or we have a bad flip. So yeah, let's actually, when we solve some problems which are sequential, as like right now we have a sequential problem, we have like those edges and we basically flip the edges in order and do a possible change. Let's consider what will happen on our first change. And like the first change comes when we do the first bad flip. So yeah, imagine we have like, yeah, I have drawn some things which probably will illustrate the things better. So initially, as I said, we have fixed edges which are from every vertex to 1. And now it happens that we want to flip the edge from 1 to x, for any x, which is from 2 to n. And like, yeah, basically we flip this edge, so now it goes down. And I mean, the problem there is the following problem, that this thing may not be strongly connected now. Like maybe it will be strongly connected, but we don't really have guarantees for it. So yeah, imagine like we have this vertex x, and there's some other vertex 3, which is directed like that, and then it is strongly connected, probably. If like you can, if the vertices 2 to n are strongly connected, then this will also be strongly connected, because you can go from 1 to x now, then you go to 3 and you go back to 1, and like the cycle, now you already have a cycle with 1, which is the thing we actually want to avoid. So yeah, instead of actually just flipping this edge, let's do the following. Let's change this set to the following. So basically, like, initially we just had 1 on top, but let's now also add x on top. And like, basically, we'll also fix the directions in the initial graph of the edges that go from every vertex to x2. So why is this helpful? Well, I mean, if you basically fix all of the vertices, which are like excluding 1, but like all of the other vertices, so like 2 to n excluded x, to be directed to x, then you know that at the current moment there is no cycle. Well, like, because I mean, you can't really, so you have like this second set, you also have like the first set, which is, I mean, you have those two sets, and I mean, like, all the edges that are directed from the second set to the first set, basically like the directions are going in just one direction, and like you can reach the, let's call this S1 and this S2, so you can reach from S2, you can definitely reach S1, but you can't really reach S2 from S1. So this will not be strongly connected, and this will be fine. So, I mean, using this procedure, we basically have a solution, but we have one pretty large flaw, which is that the second set may become empty after a certain point, because like we'll basically like just do our procedure, but now we'll just have like 2 vertices here. Then if this will basically increase the number of bad edges, because now all edges that contain x will also be bad. And like, yeah, in a way it's pretty bad, because, yeah, I mean, like, in a way, like, the main problem is that we increase the bad edges, and like at some point we can just add all of the edges from the second set to the first set. So in a way we'll have like this set, which is from 1 to n, and like the second set will just be empty. Wow. So yeah, we have empty set, and like then we don't really have any edges here. I mean, we would have wanted to have some edges, and if we don't have edges here, then we just have one connected component here, and we don't have like 2 sets, we just have 1, and then we can't really argue about whether the whole thing is strongly connected or not. But I mean, like, the construction is still pretty good, but like it's wrong, because yeah, the second set can become empty. And let's consider for how many turns, like what's the, at least for how many turns can we run this algorithm. And like it's clearly n-2, because we can run, initially the second set has size n-2, and like we can run it basically until we get an empty set. And like this will happen in at least n-2 turns. So yeah, this solution, which is just starts with 1 vertex, and we just casually add one vertex to the other component, and so on, will still work for the first subtask. So in other words, like, that's a slightly more complicated solution to the first subtask, but it still works. And yeah, the good thing about it is that we can easily fix it. And now I'm going to explain the easy fix to actually get like the 3n/2 solution. So yeah. Actually before that, let's look at basically like the graph. We actually explicitly fixed 1 to be the initial vertex. And maybe that's not the best idea, because it may turn that we have a counterexample where we just have the edges from 1 to 2, 1 to 3, 1 to 4, and so on. Like, in other words, like, if those are our flips, we are going to get the wrong answer on this test. However, if we actually tried with 2, for this counterexample, if we actually tried with 2, then we would have been basically fine, because we would never increase our set. And like, the main idea is that actually that the solution is based on this fact. So like, instead of just having a fixed 1 here, let's have an s. Like, s will be some constant for some vertex. So yeah, I'm gonna go to my notes now. So yeah, basically the solution is to choose something else instead of vertex 1 to be in the initial lonely node. And before that, I'm just gonna quickly go to see whether there are some questions. I mean, this is kind of hard question. What did you miss until now? Basically, right now I just explained the first subtask, and yeah, now we are covering the second one. So yeah, there weren't other questions, but like, yeah, let's continue. So yeah, the main idea is to actually choose something else instead of vertex 1. And like, let's call this vertex S, like the lonely vertex, which we start with. And like, on the first bad flip, we'll either have like, either A1 will be equal to S or B1 will be equal to S. That's clearly true, because, I mean, on the first bad flip, going back again, we saw that on the first bad flip, we definitely had a flip which is from 1 to some other vertex X. And like, this means that either AI is equal to X, or is equal to 1, or AI is equal to, or BI is equal to 1. So I mean, like, basically the first edge should, at least one of the vertices in the first edge should be 1. And like, yeah, that's basically it. Now instead of 1, we just have an S here, because yeah, let's just introduce a variable, because it will be easier to argue about the whole thing. And like, now I'm gonna say the solution, which is we should simply choose the S as the vertex that appears at the last time in the flip list. Because like, we know that for the first bad flip, we would have either AI is equal to S or BI is equal to S. So in other words, like, if we have, I mean, we can choose S as any of the vertices from 1 to n. So like, we look at the first edge and we basically block AI and BI to be S. Then we look at the second edge and we block basically A2 and B2 to be the S. And so on until we reach AK for some K, when we can't really block any more vertices to be S. And we choose just like one of the 2 vertices to be our S. And how many turns actually will this yield? I mean, it will actually, the main idea is that, imagine, let's consider the prefix which has n/2 edges. How many vertices overall do we have? Like, n/2 sailed down. So yeah, we'll have 2 multiplied. Actually, here maybe so I just realized that I didn't properly, I mean, so what I want to say is basically that we have n/2. Let's look at the prefix of n/2 edges. So we have like, overall, we have n vertices here. However, maybe here it would have been easier to actually explain what will happen on n/2 minus first prefix. Because there we will have 2 vertices for every edge, multiplied by n over 2 minus 1, because like that's the number of edges. Like let's just look at this prefix, and we have like, we basically have like n minus 2 vertices there. And like the thing is that that's the number of blocked vertices in this prefix, because like, yeah, in a way, like you want to maximize the prefix that won't contain any bad flips. And like, yeah, we know the fact that on the first flip, either AI or BI would be S. And like, in a way, if we just block the AIs until we can't really choose an S, we'll get a pretty good solution, because we just ignore some prefix. And like, you can notice that the prefix of length n over 2 minus 1 will contain n minus 2 vertices. So by pigeonhole principle, you'll definitely have at least one vertex, because like that's less than n. You'll have at least one vertex that's available for S. And this means that on the n over 2 sailed up, you'll have, I mean, like in worst case, your solution will, like the S, in worst case, this will be like the first flip. Maybe the first flip will happen later than that, but like in worst case, it will happen on the n over 2. Basically, like what I want to say, that we are gonna skip at least n over 2 edges. Yeah, I actually have written it here. I was curious how to say it in a good way, but like yeah, the main idea we get is that by pigeonhole principle, we just skip n over 2 edges. So that's pretty good, because like this means that if we just run the simple algorithm with S equal to this vertex, which appears latest in the list, we are gonna get the solution to the second subtask. And why is that? Because we basically skip at least n over 2 sailed down edges, and then the simple algorithm works for n minus 2, like for any m which is less than or equal to n minus 2, which means that if the whole thing will work for 3, I mean, like basically that's 1/2 of n, that's the whole n, so we have like 3n over 2 minus 3. Here you see a minus 2, but like that's sailed down, that's sailed up, and like the exact analysis just shows that. And like, yeah, we basically have a solution. Pick the vertex that appears latest in the list, and then just run the naive solution. Which is, that's what I meant by like, the solution is very simple, but you have to figure it out in a way like, it's not intuitive that this simple solution will actually work. And yeah, I'm gonna check for questions again. But it seems that there are no questions. So yeah, I guess let's get back to the final subtask, which again is very simple. And I mean, by very simple, what I mean is like, instead of just fixing a specific S, let's just choose every possible S from 1 to n and run the stupid algorithm. Then we just get like the longest, I mean, if just one of them works to have like all of the subgraphs strongly connected, you're basically fine. And yeah, that's pretty much it. You just check every possible S, and yeah, you can actually just like see whether one of them works for the M. And like the thing is that we can prove that this works if we just try all possible S. This will definitely work for M less than 2n minus log n minus 2. And there is like, the proof is left as an exercise. No, I'm just joking, but like, yeah, there is a formal proof in the editorial, and here I'm gonna like discuss the main intuition about it and why it's correct. But in general, the algorithm is pretty much this. You just choose every possible vertex to be the initial lonely one, and you just run the naive procedure. And then you just check whether one of them satisfies the constraint for M and the whole list of flips. So yeah, basically, as an informal thing, let's consider the first n-1 step, flips. And like what will happen is that we basically have a bunch of connected components. Maybe we'll have just one connected component here because we have n-1 flips. Again, let's refer to the first subtask where we form the connected components only by the flips, basically like only by the edges that are being flipped. And we kind of ignored the edges that will be in the tournament graph that are between them, like the other edges basically. And like one of the main benefits here is that we'll have at least one tree. And try convincing yourselves why. The main reason why is because like, yeah, one way to prove this is by induction. Like we have n-1 flips, and one of the connected components will be a tree. So like the extremal case is when we have just one connected component. So we have like one connected component, we have n-1 edges, so obviously then we have a tree. But what will happen when we actually have two connected components? So this means that one of the edges doesn't exist in the spanning tree in a way. So like it will either be in the first component or the second component. But wait, this means that like just one of the two components will be a tree, because like just by arguing about the quantity, you know that at least one of them will be true. And like you can generalize this argument either by induction on the number of edges or by, yeah, basically just you can generalize it. We already showed it for 1, for 2, and like the same pattern goes until like n-1 connected components. And yeah, the main idea is that it's a fact when you have n-1 edges, you'll definitely, one of the connected components is definitely a tree. It's a pretty cool thing. It's used in some problems as a general fact, and if you didn't know it, you can try proving it formally if you want, because it's also pretty useful as you get like some more intuition about trees and stuff. But yeah, that's pretty useful. And yeah, basically the idea here is that we have a tree and let's choose S from it. Also, I had to mention my informal proof, it's pretty similar to the proof by the editorial list, and it's a constructive proof. So in other words, like I'm gonna find such a vertex that will guarantee the things. And like in a way, because my proof is constructive, also you'll be able to find a solution that doesn't check all the vertices from 1 to n, but like I find a construction that shows such an S, or like an algorithm that finds an S that will give the following guarantees, but also like the previous algorithm that just checks all of the vertices still works. And also like in the beginning I actually mentioned this tedious analysis, which is Tn-5, and like as far as I know, I haven't read the whole paper, but like from what I just took a glimpse, and I think it's basically the same idea, which is use every S, and like this actually guarantees something better, which is like 2n-5. But it's hard to prove and it's kind of hard to argue about. But in general, like the construction for 2n log n minus 2 is slightly better. And also the complexity is better for it. And I'm gonna explain it in a bit why. So yeah, basically at least one of the components is a tree. We already discussed this, and we are gonna choose S from it. So yeah, let's say that we have found the tree. And like let's remember what the edges here are. It's basically the flips that happen in the prefix of length n-1 of all flips. And like let's look at the first edge from the tree that appears in this prefix. And let's say it's this one. So what we are gonna do is basically we are gonna find it. Like if you look from back, in a way what we want to have is, alright, why are we even looking at the first n-1 flips? That's mainly because we want to get something that's like 2n minus something, right? So in a way, like you want to find such a choice for S, so that after this prefix of n-1, our algorithm will be able to, like in a way, stay alive, or like it will be able to go for at least another n turns. Maybe not n, but like another n-2 or n-10, or something like that. But yeah, that's why we are looking at this prefix of n minus 1, because like in a way we are going to be able to choose like we are going to build some components on like the upper side that will actually guarantee that our algorithm will be able to proceed for another n minus step. Like the naive algorithm will be able to proceed for another n minus something steps. But yeah, going back, like basically we have this edge and we erase it. So in a way, like what I mean by erase, we are going to start from the last edge in this component, and then we are going to just take it back, and we are going to consider what happens before it. And what do I mean by that? In a way, like basically, when we remove this edge, we'll have two components. And like, let's just get the smaller one, either this one or this one. In this case, it's like the green one. But like, this procedure is actually gonna end in at most log steps. And like, what I mean by this procedure, after we get this component, we again find the last edge in the prefix that appears in this smaller component, and so on and so on. And in the end, we are gonna get a single vertex. That's S. And like, the thing is that I already said that the whole procedure will end in log steps. And let's look at the procedure in the backwards order. So like this will be S, which is the final vertex. And then at some point we had like S connected with one edge, like with one flip to some other component. Like that. But we just decide to choose S. This means that, think about the naive algorithm. Because like we were looking at the edges in backwards, like we always chose the last one, then the last but first that appears, and so on. And like the main idea is that this way, if we then go in the right direction, starting from the choice of S, we are gonna, in a way, like just build up the component by just adding the edges and adding the edges and adding the edges and so on. And what will happen is like, we have S, we look at the first edge we basically add it here. And like what will happen is that in the naive algorithm, we'll just move the other vertex, if that was S, and that was some X, we would just move X to that direction. And I mean, like, if you just look at these steps from beginning to end, what will happen in the end is that obviously we delete in this way at most logarithm number of edges. Because every time you just take the smaller component, and then you know that the other component is larger than it. So like the size of this component is less than the overall size over 2. So yeah, in other words, like this means that every time we just add a single vertex to the right side, like that, and so on, and like we'll have at most logarithm number of edges in the prefix of length n. So yeah, we just like have the connected component here, which, I mean, like after we have built the prefix, and like you just choose the direction to just go inside of this component. And I mean, that's pretty much the solution. Like, to be completely frank, like we just always have the size of the component, and like by looking, we just look at the last edge that appears in the prefix, and we choose the smaller component, and so on and so on and so on until we get like a single vertex S. So yeah, basically, like after the prefix, the component of S, like by component I meant like going back to the explanation here. So yeah, the component of S here had like 1 and X, and like in the prefix of length n minus 1, this component will have just size logarithm. And this means that, going back again to there, I shouldn't have scrolled so much, but like still, this means that we can run the naive idea for an additional n minus 2, that's like the overall number, minus log n, because like the size is the logarithm of n, and we can just run our algorithm for some additional steps. And basically this means that we get the required f of n constraint, because we had the prefix of n minus 1, which we skipped. So it's like n minus 2. Actually here it's n minus 1 here, because this contain, like the logarithm actually contains s. So yeah, it's n minus 1 minus log n. So yeah, we can run this algorithm for that many steps, and yeah, basically we also have this n minus 1 steps in the beginning. So this gives us like the 2n minus 2 minus log solution. That's the construction, and like the proof is by construction. And yeah, still you can just try the idea where we try all possible vertices S, and it will work. And like the complexity is, using the construction you can actually find the vertex, like the S vertex in On, but then you still need n squared to actually print the output. While if you just use the approach for every possible vertex being S, you will have a clear n squared. Actually it's nm, but like we know that m is equal to a polynomial of n, like a linear function of n, so yeah, the whole thing is n squared. And yeah, that's pretty much the solution. And I hope you enjoyed. Now I'm gonna be around for some questions, because maybe I rushed the last part a bit, but I'm pretty sure the last subtask is actually basically the first subtask plus the proof. If you want a formal proof, look at the editorial, because yeah, I mean, the tutorial has like the formal proof, and like the main idea, maybe because like to visualize the whole thing, is that we go from the back to actually look what the edges in the prefix of length n minus 1 will be, and yeah, then we find a certain s, and then from this s we just look at the component and run the naive algorithm. But yeah, also like as I said, there is this paper which shows f of n equal to n minus 5. It's linked in the editorial too, so yeah, you can check it out. Basically, as far as I know, it's just a proof why if you choose every possible, yeah, basically the main idea, you just use every possible s, and then you just check whether each of them satisfy your decision, then like this will be fine. So yeah, let's now look at some questions. Okay, I mean, thanks for the feedback. Also, like, there will be a feedback form, so I mean, just like in general, feedback is very welcome. Yeah, in general, feedback is helpful. But yeah, I guess I'm gonna wait for another 2 or 3 minutes just to see for some other questions. And if there are no questions, I'm gonna probably end the stream. And I hope you enjoyed the explanation. I tried making it as simple as possible, and I think I did a decent job. Hopefully that's the case. If not, I'm gonna try better next time. So that's why feedback is greatly appreciated. But yeah, maybe I can end it by, if you have some questions, just put them in the chat, and while you're basically writing them, maybe I can say some good takeaways from this question that can be used in the future if we solve some other problem. So obviously, maybe the first one, if you're not familiar with it, it's very important to know that when you have a graph with less than n minus 1 vertices, so yeah, you have a graph with n vertices and less than n minus 1 edges, you definitely have at least 2 connected components. And some constructive problems use this fact, and it's pretty useful, as you can kind of hide some information. Even some problems can just leave this thing in the constraints, and this way they hide some parts of the problem statements in the constraints, and you have to realize that. So yeah, that's a pretty good thing to know. In a way, like it's kind of obvious, but like if you haven't seen it before, maybe you won't really notice it. So yeah, that's a good takeaway. Then I guess the other one is basically to think of some simple ideas, because like in general the whole algorithm and solution is very simple to implement. It's very simple as an idea, but I even think that quite a lot of people thought of this idea, because like when you think about it, maybe your first idea would be you just pick some vertex, and then like when you just force everything to go into it, and like when you see something that's flipped, you just also force the other vertex. And like that's maybe one of the most basic ideas for this problem. And if you just try forcing with every vertex, that's the solution. So for 100 points. But like most likely a lot of people just thought, oh well, that's like the last problem, it can't be this thing. But it is. And yeah, the proof is pretty cool. And yeah, maybe the other thing you can take away is that if you have a graph with n-1 edges, just any graph, then it will have at least one of its connected components will be a tree. And this is again pretty useful. This is actually even useful in some graph problems. As far as I know, like I have seen some problems where you just use this fact to actually build some construction where you just start the construction using the tree, and then, for example, you may connect the other components to the tree. But yeah, it's another pretty cool fact. It's also kind of obvious, but yeah, if you haven't seen it before, maybe you won't realize it. But yeah, I hope this is helpful. Maybe you will use it in the future. And yeah, I guess there are no other questions, so I guess I'm gonna end the stream now. So thanks for watching, guys, and yeah, I guess see you next time.